Hello students, welcome back. Now let's go to section 4, Library of Functions. Here's a list of functions that we want to review. Linear functions, quadratic functions, and power functions. I hope everybody remembers everything, and I'd like to go rather quickly. And then polynomial functions. Well, we need some talk, but don't worry, I'm not going to go too deeply into this. And the same goes for rational functions. And of course, if you want to skip, go ahead and skip rational functions. Can be too hard. And exponential and logarithmic functions. Well, they are important, but not for now, at least not just yet. We're going to go deeply into exponential and logarithmic models in week 9. Until then, only bits and pieces of exponential and logarithmic functions will appear. So it's not going to be too bad until that point. Okay, let's begin. Let's begin with the linear functions. And here is the standard form, or the slope-intercept form. Running through 0, b, the y-intercept right here, negative 0.6 approximately, and the slope in this case is negative 1 approximately, which means as I go one step to the right, I have to go up by negative 1 step. What do you mean negative 1 step up? I have to go down by 1 step, approximately speaking, of course. Run it again. Okay, this time I have positive slope running through 0, b here. As I move 1 step to the right, I have to go up by 1.82 steps, approximately. So that's the slope-intercept form, or equivalently, the standard form. And the next one is the slope point form, which is the most important form for this course. For algebra classes, usually this was the most important and called the standard form. But here, this is our golden standard now. This is the most important form. Slope m and running through the point x0, y0. You can write it this way, or flip this y0 to the other side and write that way. Either way, it's the same thing. Which do you prefer? I usually do it this way, but many students do it this way too, including my son actually. He prefers the latter form. Now here's an example running through this red point, x0, y0, and the slope is 0.93 something. Let's run it again. We're going to get different point and different slope, like this. In any case, we follow the same form. Remember this because that's the most important equation of the line for this course. Now, the 2-point form, and in the slope point form here, instead of x0, y0, put x1 and y1. We get this form. And then what is the slope? Slope is rise over run. The difference of y-coordinate over the difference of x-coordinate. Put it in there, y2 minus y1 over x2 minus x1, and voila, we have the 2-point form. So here we go. The slope is the difference of y-coordinate over the difference of x-coordinate. Rise over run. Rise is difference of y-coordinate. Run is difference of x-coordinate. Let's run it again, and you're going to get something like this. Like that. Okay, something like this as well. Negative slope. Anything can happen. Those are 2-point forms. The final topic, the average rate of change or the slope. Slope of the line, rise over run, the difference of y-coordinate over the difference of x-coordinate, delta y over delta x. And if you have coordinates explicitly written down, that's y2 minus y1 over x2 minus x1, like that. But me, I prefer this form. Delta, the Greek letter delta, means the difference. So whenever I see delta, I'm subtracting one from the other. y2 minus y1 or y1 minus y0, whatever the indices are given. Same goes down there. Do not cancel deltas out. Delta is not a separate quantity that you multiply to x or y. Delta means take the difference. Okay, so much for linear functions. I know there are a lot more, but we're just be reviewing the essentials only. Now let's go to quadratic functions. Here is a general form. Ax squared plus bx plus c, or is the standard form? I don't know. Which one is this standard form? I don't remember. I'm definitely certain this is called a general form. Anyway, here are a couple of examples. When the leading coefficient a is positive, we have positive 2 here, then concave up. When the leading coefficient a is negative, then we have concave down like this. When a is equal to 0, of course, then that's not a quadratic function because this is 0. This part just drops out. That's 0. So we have a linear function. Alright, so much for the general form. Another form that you have to remember is the vertex form, the latter form here. Same A, so it determines concave up versus concave down, and then h comma k is the vertex. Like this, h comma k, negative 1 comma negative 3/4 in this case, and positive 1 comma 3/4 in that case. And they're both given in the general form. Well, if you do the vertex form, it's going to be like this. 1/2 x minus of negative 1 squared minus 3/4 y equals to 1/2, negative 1/2 this time in the right hand side, x minus 1 squared plus 3/4. So this one here, I can see that whether we have negative 1/2 here because we have to have the same a value there. The others you can algebraically manipulate, and we end up with h comma k like this. So 1 comma 3/4. So h is 1, k is 3/4. Plug everything into this. Same goes over here. But of course, nobody writes like this. Negative of negative 1, nobody writes like this. It's going to be better if you rewrite it like this. How did I lose color? Okay, there you go. These are the vertex forms, and these are the general forms of the same function. How do I convert one from the other? Whether you can convert those using complete square or these formula, it doesn't matter. Just do whatever you want to do. H is negative of b minus 2a. K is negative of b squared minus 4ac over 4a. There's a proof for a vertex formula if you're interested. And another way to understand those is through graph transformation. Again, if you're interested, go through these, and you can recall those from prereq courses, either in college algebra or STEM algebra or business algebra or algebra for teachers, whatever algebra. Another form for quadratic functions that is relatively important is the intercept form. Like this. Factor out, then you can rewrite like this, and if you set it equal to 0, what happens? Something times something is 0. One of them has to be 0 because there's no way you're going to get 0 by multiplying a bunch of non-zero numbers. So if this is 0, we have x equals to r. If that's 0, we have x equal to s. So we have two x-intercepts like those. And here, whether this and that, this and that. And by symmetry, we must have the vertex right in the center. The average of r and s, r plus s over 2, that's my h value. And then plug it into this expression, and I'm going to get h value. Another important thing is that, let's see, if we have two real zeros, we get like this, like that, two x-intercepts. And that corresponds to b squared minus 4ac is greater than 0. You see, here negative of this positive quantity is down here. Or when denominator is negative, then case over a positive like this, either way, they all correspond to b squared minus 4ac is greater than or equal to 0, and that corresponds to the quadratic formula plus of square root b squared minus 4ac. And as for the other cases, if b squared minus 4ac is less than 0, then the square root does not make any sense, so no real root, and not coincidentally, we have no crossing. In this case, just touching, we have double zero here. In this case, R and S are the same. They merge together, a same value at H, and we have double zero like that. That's about it. The details are left to the students. After all, I don't want to repeat the 2.5 weeks of studying in intermediate algebra and again in college algebra, again here. So if you're interested or if you need some review, go back and do it on your own. Now the next topic, let's go to power function. The simplest is the monomials, x to the whatever power. For odd power, we're going to get something like this. First power is an exception. We have a line, otherwise we have curves. And please notice that the higher the power, the flatter it gets around the origin. And as a computation, this shoots up more rapidly or shoots down more rapidly as I move away from the origin. And the range is negative infinity to positive infinity. Go down to negative infinity, going up to positive infinity, you can easily see those. For even powers, on the other hand, we get all these only above the x-axis, so the range is 0 to positive infinity. Second power, fourth power, sixth power, and so on. As the power increases, the flatter it gets around the origin, but as a compensation, they shoot up more rapidly away from 0. Some symmetries, let's see. Odd functions and even functions corresponds to odd powers and even powers. Symmetric with respect to the origin versus the symmetric with respect to the x-axis. And if you're interested in the proof, there they go. Basically, -1 to odd power is negative. -1 to even power is positive. That's basically it. Radical functions, and one part of parabola and one part of this fourth power function and so on. And these are odd radicals. Just tilt to graph. Fractions are also powers. Whenever you have negative power, we have a power in denominator, so we have fraction. In that case, denominators cannot be 0, so you have vertical asymptote forming around x equal to 0. And in general, we have x to the m over n power. That, as a matter of fact, is, this is, let's see, nth root of x to the m power. And in this case, we consider positive x values only. Here's a program to visualize some arbitrary powers. Depending upon what m over n value is, we get different graph. Okay, so much for power functions.